This substation lattice represents the physical scale of a massive national project. For decades, the American power grid functioned as a reliable 20th century marvel, wiring the continent and supporting years of industrial expansion. The original architecture succeeded because it relied on a static baseline of demand. Planners designed the system for predictable rhythms: homes, offices, and small-scale factories that drew power in steady, well-understood patterns. Those patterns no longer hold. The modern grid now supports massive data centers, automated logistics hubs, and hyper-connected manufacturing facilities, forcing aging infrastructure to carry loads far beyond its original breaking point. Relying on a framework built for the past to handle the exponential weight of a digital future guarantees structural failure. Managing this strain currently relies on brute force. Network operators push energy through stressed corridors to meet sudden spikes, which triggers the latency bottlenecks and systemic instability we see across the country. Unpredictable power creates cascading risks in zero-fail environments. In this hospital ward, life-critical systems and emergency response units depend on a foundation that does not drift. This fragility functions as a hidden tax on the economy. When developers cannot guarantee power stability, they rely on expensive guesswork, which often results in stalled industrial projects and paralyzed capital investment. The real threat is not a localized blackout, but the total economic paralysis caused by a national foundation that lacks deterministic behavior. Rebuilding the grid requires a transition from reactive physical guesswork to mathematical certainty, verifying outcomes before a single wire is laid. This animation illustrates the transition to deterministic modeling. Chaotic pathways snap into a rigid, geometric structure, a reversible computational substrate testing breaking points without lossy approximations. This allows multi-scale simulation, maintaining stable energy transport across entire urban landscapes. This intelligence layer eliminates the cost of complexity by proving the physics of the grid before capital is deployed. We can forecast exactly how a sequence of loads will behave over long horizons. Absolute software predictability provides the essential raw material required to stabilize our physical world. Historical grids relied on manual monitoring and reactive controls, like the analog dials in this room. A deterministic substrate replaces that manual oversight with mathematical clarity, providing a stable foundation for the network. This clarity allows for the safe integration of large-scale clean energy sources, and significantly lowers the cost of network expansion by removing trial-and-error engineering. Look at the immense physical capital at risk in a project of this scale. Predictive stability prevents the costly redesigns that often occur when a project moves from a theoretical model to physical construction. Mathematical certainty allows for the design of hyper-ambitious infrastructure, ensuring these systems remain stable under the most extreme conditions. Secure planning provides a definitive signal to private markets, unlocking the capital investment required to scale national systems. That investment mobilizes the trades. When the planning is deterministic, utility linemen can get to work physically rebuilding the grid, with the confidence that the architecture is sound. Deterministic tools empower the modern American builder. Like this ironworker, these teams can fix failing infrastructure correctly on the first attempt, because the underlying math is unshakable. Achieving mathematical certainty functions as the economic trigger for national labor. The electrical grid remains the active frontier for large-scale innovation. A modernized grid ensures supply chains and heavy manufacturing lines operate at maximum scale. Predictable power enables this kind of complex, high-output industrial coordination to run flawlessly. The intelligence, manpower, and exact computational architecture required to start this renewal already exist. American growth and prosperity begin the moment we anchor our national systems to a mathematically unshakable foundation.